Welcome back, everyone. In this section, we're going to talk about probability. So the probability of some event occurring is just a number that describes how likely it is for that event to occur. What we call a probability experiment is just a process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. Examples of probability experiments include flipping a coin, rolling a die, drawing a card from a deck. In these experiments, we can predict what outcomes are possible, but we can't predict with certainty which one's going to happen. We say essentially the outcomes occur at random. In any of these probability experiments, the set of all possible outcomes is what we call the sample space. And so we're going to start by just practicing with what a sample space is. So when you toss a coin, there are a total of two possible outcomes. You can have heads, or you can have tails. This is your sample space for when you flip a coin. When we write a sample space, we write it as a set of numbers or a set of values, so with brackets and commas separating them. But this is our sample space for flipping a coin. When we roll a die, there are 6 possible outcomes. And if we list those, it's 1, 2, 3, 4, 5, and 6. Those are all the possibilities that you can have when you roll a die. So let's just look at these briefly and determine the sample space. Again, if we roll a single die, the sample space is going to be 1, 2, 3, 4, 5, and 6. For a true-false question, true or false, you only have 2 possible outcomes. And so the sample space is going to be true or false. If we flip 2 coins, well, now there are 4 outcomes. We can either get heads both times, we can get heads first and then tails, tails first and then heads, or we can get 2 tails. And so the sample space just represents all the possible outcomes of a particular experiment. What we call an event is any subset of the sample space for some probability experiment. An event could be a single outcome, or it could be a combination of several outcomes. For example, when we roll a die, there are 6 possible outcomes, but when the number is odd, there are a total of 3 outcomes. For a die, that would be 1, 3, and 5. So there's a small distinction between an outcome and an event. An outcome is a single occurrence, while an event can contain any number of outcomes, depending on the situation. For example, rolling a 2 on a single die is an outcome, because it's one single occurrence, but it can also be considered an event. Rolling an odd number, on the other hand, is an event that's made up of 3 different outcomes, 1, 3, and 5. So by itself is not an outcome because it's made up of more than one outcome from the experiment. So let's recall the sample space for flipping 2 coins. We can get heads, 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 tails, tails, heads, or tails, tails. How many results match getting heads on the first flip and tails on the second? Well, heads on the first flip and tails on the second, that is only one of the results. And so this is an outcome, one single piece of the sample space. Now, how many match getting 1 head and 1 tail? Well, there are 2 of those. And so getting 1 head and 1 tail would be an event. So if there's more than one way for it to happen, it would be an event and not an outcome. So here we just want to identify the difference between outcomes and events. When we roll 2 dice, getting a 3 on the first die and a 5 on the second. Well, there's only one way to get a 3 on the first roll, and there's only one way to get a 5 on the second roll. So this would be an outcome because there's only one way to do it, but we can also consider a single outcome an event, so this one would be both. When rolling 2 dice, getting a total of 10, well, there's a lot of ways to do that. 5 and 5, 6 and 4, 4 and 6, and so this would be an event, because it encompasses more than one outcome. The same goes for when flipping a coin 10 times consecutively. There are numerous ways to get tails 8 times out of the 10. We could get tails the first 8 times, we could get heads and then 8 tails, and so on. There's numerous different ways, so this would still be an event, encompassing numerous outcomes. When we discuss probability, there are 2 ways we can look at it. The first is what's known as theoretical probability, which is predicting what's going to happen before we've done any type of experiment. we're theoretically going to determine what the probability of a particular outcome might be. What we assume in this case is that every outcome in the sample space is equally likely. So if we flip a coin, heads and tails is equally likely. When we roll a single die, all of the numbers 1 through 6, they're all equally likely. If you randomly choose a card from a deck of 52, all of those cards are equally likely. And so that's the main assumption that we're going to make when determining the theoretical probability. So if you flip a coin 100 times, about how many times would you get heads? We know that if you flip a coin, you can either get heads or tails. Because each is equally likely, that's our assumption, then we know we're going to get about 50 heads and about 50 tails. So what percentage of the time would you expect the coin to land heads up? If we expect to get 50 out of our 100 flips, then this would be about 0.5 or about 50%. So about 50% of the time, we'd expect to get heads. About 50% of the time, we'd expect to get tails. We use a coin flip as an example because it's a simple example of just two possibilities, and because it's something you're familiar with. But in general, the probability of an event E in some sample space is just given by the number of outcomes in E, the number of outcomes in that event, how many different ways it can happen, divided by the total number of outcomes in the sample space, the total possibility. And so, as we saw in the previous example, to find the probability of heads, well, we expect that there would be about 50 heads out of 100, which is 0.5 or 50%. So let's say we roll a fair die, and we want to determine the probabilities. The probability of rolling a 2. Well, our sample space for a fair die, we're just going to write that up here. 1, 2, 3, 4, 5, and 6. The probability of rolling a 2, well, there's only one 2, so there's one outcome out of a total of 6 in the sample space. So the probability would be 1/6, or we can convert this to a decimal and then to a percent, 0.1667, or about 16.67%. The probability of rolling a number less than 5, well, there's 1, 2, 3, 4 numbers that are less than 5. So 4 out of the total of 6 gives us a probability of 0.6667, or about 66.67%. The probability of rolling an odd number, well, 1, 3, and 5 are all odd numbers. 3 out of 6 would then be 0.5, or 50%. So if we want to find the sample space for when we flip 3 coins, we can use a simple process that we'll talk more about in the next section, known as a tree diagram. We know that the first flip can either give you heads or tails. And then from that, each consecutive flip will either give you heads or tails. And so we can use this method to determine our outcomes and our sample space. So, our possibilities, heads, heads, and heads. So, 3 heads. Then heads, heads, tails. And we just follow along the lines to find our possible outcomes. Heads, tails, heads. And then heads, tails, tails. So these are our 4 possibilities. If we roll a heads first, if we roll tails first, we could get tail, heads, heads, or tail, heads, tail. Or any of these other 2. And so now we have our 3 coins that are flipped and the 8 possible outcomes from our 3 coin flips. So now we want to find the probability of each of these events. So if we flip 3 coins, what's the probability that we would get at least 2 heads? So looking at our sample space, how many of the outcomes have 2 heads? Well, 1, 2, 3. So there are 3 possibilities out of a total of 8 outcomes, which is equal to 0.375 or 37.5%. At least 1 head. So that means the only one that's not going to work is just when we flip tails 3 times. So there are 7 outcomes that have at least one head out of a total of 8. 7 divided by 8, 0.875, or 87.5%. And then finally, at most, one head just means that it can't have 2 or 3. And so we can cross out anything that has 2 or 3 heads. And that leaves us with 1, 2, 3, 4 outcomes out of the 8, or again 50%. Just a few things to recognize about probability. Probability is never negative, and it is never greater than 1. Probability will always be between 0 and 1. When there's an event that can't possibly occur, its probability is 0. When it's guaranteed to occur, the probability is 1. And then the last piece is that if you add all the probabilities for every single outcome, the result always has to add up to 1. You know that something is going to happen. One of those outcomes is going to occur. And so if you add up all the probabilities, they should always be equal to 1. We generally express probabilities as fractions or decimals between 0 and 1, or as percents between 0% and 100%. If we say the probability of an event is 1/2, then there's a 50% chance that it'll occur. If we have a probability that's very close to 0, then it's unlikely to occur. If it's close to 1, then it's very likely to occur. So the greater the probability, the more likely that event is to occur. Sometimes, however, it's easier to determine the probability of an event if we know the probability that that event will not happen. So for every event we have in some sample space, the set of all of the outcomes that are not in that event is called the complement of that event. The probability of an event plus the probability of its complement would be equal to 1. One of the two things is going to happen. If we know the probability of that event, then we can determine the probability of the complement, or the other way around, by just using this formula. By just using 1 minus the probability of the event we know about. So for example, we know the probability of rolling a 2 on a single die is 1/6. What's the probability of not rolling a 2? Well, that's 1 minus the probability of rolling a 2, or 1 minus 1/6, or 5/6, or 83.33%. So of the next 32 trials on the docket in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. If jurors are assigned to trials randomly, what's the probability that a given juror won't get a homicide case? And so there's 2 different ways that we can calculate this. First of all, if we want to know what's the probability that the juror won't get a homicide case, that means we want all the cases that are not homicides. So there are 12 drug offenses, 6 assaults, and 9 property crimes. If we add all of those up, we find that there are 27 other types of cases. 27 that aren't homicides divided by 32 will give us the probability of randomly choosing one of the cases that aren't homicides, or 0.84375, or about 84.38%. The other way we could do this is find the probability of them choosing a homicide case and then doing 1 minus that probability. So there are 5 homicides out of 32 cases. The probability that you randomly choose a homicide, 0.15625, and then to find the probability that it's not a homicide, we're just going to do 1 minus the probability that it is. And if we do 1 minus 0.15625, we're going to get exactly the same answer, 0.84375, or about 84.38%. Empirical probability is based on observed frequencies using experimental data. So whereas theoretical probability, we predict what's going to happen before we do an experiment, the empirical probability is measuring what happened after we did the experiment. So suppose out of the last 100 days you've gone to the gym 60 times, it'd be reasonable to guess that the probability of you going to the gym on any random day is 60 out of 100, or about 60%. What we call the observed frequency is the number of times a particular event occurs out of however many trials. The observed frequency of going to the gym in this case would be 60. 60 out of 100. The observed frequency of not going would be 40. And so if you add them together, you get the total number of trials. So if we want to find the empirical probability, it's just the observed frequency of some event divided by the number of trials. Very similar in a way to the theoretical probability, except that this one is based on actual measurements, whereas the theoretical probability is based on the assumption that all of the possibilities are equally likely. So we flip a fair coin 150 times. The number of heads and tails is given below. So let's determine the experimental probability. Well, for heads, if we flip 81 out of 150, we find that we get 0.54 or 54%. For tails, 69 out of 150, 0.46 or 46%. Well, remember, the theoretical probability in this case is 50-50. You would expect to get about 50 of each, or in this case, 75 of each. But what you expect theoretically and what you determine experimentally are not always the same thing. The theoretical probability gives you a general idea of the possibilities that will occur, but when you actually do the experiment, things are not going to work out exactly that way. There will almost always be some differences. Please let me know if you have any questions.